आगे हम आगे down my friend. How my hair turned grey waiting for the stream to start. Yes, bro, it's not easy to set this things up, bro. It's not easy. I was getting this mic set up last time, like I did the last time. I don't think you were there. So like right before the stream, like it was supposed to happen at 6 p.m. or something, and like right before the stream, like 1 hour just before the stream, I just updated my graphic driver, and like shit went boom. My GPU wasn't responding, camera wasn't working, mic went boom. Like it was a fucking mayhem, bro. But how are you, my dear friend? तो सोने जा रहा होगा, रात हो गई होगी तेरे यहाँ. Zindaya, bro, are you alive? Daud, my friend, are you alive? Like if anyone is watching, please let me know if the audio quality is fine or not, or I'm just blabbering. थोड़ा लेट से सोता हूँ. Okay. Did you get your gym in today? Fuck this fucking one. Shit. Did you get your gym in? Canada shift. हाँ रही आवाज bro. बस यही तो चाहिए bro. Is there echo in the voice? Like I don't know. Is it clear? आवाज तो आ रही होगी, but is it clear? Is it clear enough? Respond, bro. Respond. Must be clear. Okay, let's get things started. लंदन में बैठ कर के भी my buddy is still using Oya and Cosmic. yeah bro, like RGB for extra FPS. वही सुन रहा हूँ. Okay bro, okay, let's get this started. Okay, how do I share my screen? Yep. Audio input. Venom's tech, yes bro, Venom's tech. You got that joke, bro. Venom's tech. Yeah. Whenever like I buy a product, I just go review the Venom's tech. Here's the best reviews. Okay, display capture not available. Why the fuck not? Yes, entire screen. Okay. But like now I have two screens, so shit is a bit convenient, I would say. This shit is convenient. What did I do wrong? Okay, I did something that where did that window go? Come on, buddy. Yup. show me. Yup. Oh, where are my notes? So we are going to see some differential geometry, like last to last stream, if you guys were there. Not no, last to last streams I did some quaternions. Okay, last stream, if you guys were there, you might have seen some stuff, but the audio was fucked, so I'll just go over it quickly again, and let's see if I can get to the part where like we describe a surface using mathematics. Fucking mathematics. Okay, why is this thing not visible on the screen? Come on, bro. Oh shit. Wait. Display capture. Primary monitor. Yup. Now it should be fine. Come on. Yep. Minerva, like the SAP ERP might get right. Yep. That's basically it. Where did we show you? If it's here. Fuck. But yeah, that. Yep, this is our Minerva portal. You can access all the modules here. It's like a portal from KIIT. Actually, we are done with one of our modules. Like, which one was it? This Foundations of Computer Graphics. So what these guys decided, right? Okay, so this sem we have like 3 modules, and they ran one single module for an entire month. Like we had 9 to 10 lectures per week for this module, and in the entire month we finished the lectures, the labs, assignment. It's done. It's a done deal. And we don't have exams. It's just assignment based. But like those assignments are fucking brutal, bro. Absolutely brutal. Wait, can I show? Okay, I can't show you my programming assignment because it's on Linux. Maybe next time. But let me show you like the sort of maths that we do. Okay, where do I start this thing from? Let me pull up my notes. Wow. Nope. Modules. Foundations. Slides. Differential geometry of curves. Come on. Yep. I'll just this is what we did like in the last stream, but like I tried to do it, but I'll just go over it quickly. So what the fuck this is about? This is how do you define a curve? This is what it's about. And like why do we care? So like if you see this function f of t, comma t, if you like plot it on a 2D axis, and so like if you say 1 comma 1, then you will get a point somewhere around here. And like, can you see my mouse cursor? I hope you can. Yep, I hope. Yep. So if there is a point 1 comma 1, then it will be here. It's 2 comma 2, it will be here, minus 1 comma 1. So you see this black straight line. Yep, that's your fucking f of t. And fuck you. And if g of t is t square, so it will be like 1 comma 1 will be somewhere around here. Everything which the f of t had, but it won't have the negative part, because if you substitute like minus 1 comma minus 1, it will be 1 comma 1 only, because it's squared. But h of t, which is t cube comma t cube, will be the same curve as t comma t. And since like we have multiple versions of we have multiple representation of the same curve, that's why we need a way to describe these curves that is unique to them. And like that's where like this ALP comes in. For a we define like ALP is L of t 1 over root t to t by t. Okay, how did we come to 1 by root 2? Yep, wait, I can show you this one. Why do we define? Maybe I should just start coding, bro. Yes, I can see the cursor. Yes, my boy. Yes, my boy. You can see the cursor. Wait. Yep. Yep. So it was like come on. F of t was like what was the function? T comma t. And like so ALP is defined by like how far we have traveled along the curve at a constant speed 1. So if this is the function, and like if we take the mod, it will be like t fuck 1 square plus 1 square, which is root 2, which is equals to 1.41 something something something. But like by definition, the ALP arc length parameterization tells us like how far we travel along the curve at a constant speed 1. So but it's like 1.41 something something something, and which is greater than 1, meaning we are going too fast, and we don't want that. So what we do is like we divide the function by fucking root 2, and we get t by root 2 comma t by root 2. Sorry, with bad handwriting, bro. t by root 2 comma t by root 2, and that's the ALP for this curve. But why do we care about this stuff? We'll get to that. We will get to that. Okay, so that's how it was 1 over root 2. And then this is the arc length integral. So if you have to find what's the distance covered by this, what's the length of this small curve, then okay, something happened. Oh no, okay, it's alright. चॉकलेट बॉम्ब बचा है, आशीष कुमार चॉकलेट बॉम्ब बचा है ब्रो। भाई मैथ्स पढ़ा रहा, सोचा था गेम खेलेगा। No bro, it wasn't a game. I'm not doing a game stream, bro. It's work related stuff and me trying to recap shit. But maybe I actually want to cover this differential geometry and then maybe one more topic, mesh data structures. Like that's one of my favorite topics. And after that, I'll just jump to like maybe 2-3 streams later. I'll just be coding here. But for now, suffer, bro, as I have been suffering. So, how do you find this length? Well, you must have learned about this in your 10th, 11th, or somewhere around those times. You must have seen this. How do you integrate? It's something called integration. So you integrate along this. You take a small distance dx and find the length over that triangle and like integrate over a to b, and yeah, you're the fucking length. Bro, every single mathematics concept that I thought like I will never see again in my life, every single one like comes one day or like 2 days later and slaps me like, got you, motherfucker. This shit is crazy, bro. It gets crazier every single day. So yep, that's what this is, the length. And like you take the, I'm going very fast actually because I already covered this stuff last stream, so I'm going fast. I want to get to the good stuff today. So you take the mod of it, yeah, you get 1 square plus f dash x dx square, rewrite it, ding 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 ding. So when you take the differentiation of the curve, like you differentiate it, you get the velocity vector, and you have the velocity. If you have the velocity vector, so it has a direction associated with it, so that's pretty helpful. Why, we'll see in a few moments. And we define the ALP to be the parameterization, where the parameter t is the length, f of u equals to, yeah, u equals to f dash. Okay, what does this bold face f means? It's in a vector space, so it's, imagine like it has coordinates xyz. That would make more sense to you. But like, yeah, bold face means it's in a vector space. So define the LP to be the parameterization, where the parameter t is the length. Okay, that is f of u such that u equals to length of f dash t, where you, okay, wait, I must have written something. Yeah, it's the same thing. Why am I repeating this? Yeah, there is always an ALP. Okay, for a given curve there's an ALP, but we might not be able to find it. It is what it is. And in the ALP, like the length of the direction vector is going to be always 1, because remember how I told you, like we want to tell like how far we have traveled the curve with a constant speed 1. So ALP, that's how we defined, and that's why we did this fucking root 2, because we wanted the length to be the constant speed to be 1. So the mod of the differentiation, because like remember, like if you take the mod of if you take this derivative of the curve, you get the velocity. Like take the mod, you get your speed, and speed will always be 1, because that's how we define the ALP. All right, so if you so that's how like f dash u mod is equals to 1. And like what did we do here? Substitute the definition of mod v. Okay, what was mod v? Okay, root over 1 square plus f dash x dx square. Okay. Okay, this can also be written as a dot product of he has written like f dash u dot f dash u, it's the dot product. If you like solve it, yep, it will collapse to this. Square both the sides, yeah, we got rid of the square roots, derive both sides, da 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 da. You get f double dash u. Okay, what is f double dash u? F double dash, so like if you differentiate it once, you get the velocity. If you differentiate again, you get the acceleration. Physics, probably 8th, 9th, 10th class, I don't know, somewhere around that. But yeah, you get you have an acceleration. And why do we care about it? I'm getting to it. So it collapses this to this f double dash u dot f dash u equals to 0, and which means okay, the only condition, like when two vectors dot product is 0, is that will happen only when both of them perpendicular. So f double dash u dot f dash u equals to 0 means these both are perpendicular, and meaning the velocity vector and the acceleration vector are perpendicular to each other. And we call this acceleration vector as a principal normal vector. So now if you like have one vector which is acceleration, like I will use this hand, I hope you can see it. So you have this acceleration velocity, and like you have an acceleration. You take the both are perpendicular to each other. Now if you take a cross product of them, you get a third vector which is perpendicular to both of them. And like if you have these three vectors perpendicular to each other, you have a orthonormal basis, which is very helpful in moving an object, rotating an object, doing all bunch of shit, transformation matrices and all. But more importantly, like if imagine there is this curve, right, and like your object is moving along this curve, like imagine a fucking roller coaster ride. Oh, how many people are there? Oh, it's just me, I'm talking to myself, fuck it. So imagine a bunch of imagine you're on a roller coaster ride and you're moving left, you're going along the curve. Wait one second. Yeah, imagine you are along the curve moving, and like then if you have a velocity vector and the acceleration vector, yeah, and you can get the third vector by the cross product, the normal, and yep, you can rotate along the curve. It helps in that. It helps in the transformation matrices. F dash I normalize to get the finite frame light curve. Okay. Also, like this is where he goes on to show that if you are like turning very fast, so the curve that it will form will be a very small, I mean like you could fit a very small circle, and like if the curve is not too tight, if the turn is not so sharp, if that makes sense to you, uh, well, you can fit a bigger circle. What does that mean is, imagine if you are turning, like doing a very sharp turn, you will have to apply a lot of a more acceleration, and more acceleration means tighter curve. So the radius of the curve becomes inversely proportional to the magnitude of the acceleration, which is your f double dash u. Yeah, this is what it is. Yeah, this is where I wrote like kappa u equals to 1 over f double dash u. Kappa u is the radius of curvature, the curve that this thing forms at the tangent, and it is inversely proportional to the acceleration vector. Yeah, do you know, like this one, the professor wrote like 1 over kappa, and like it just messed with my head. I mean, like it was. Let me show you. Come on, boy, open up. Yep. So it was written something like 1 over kappa equals to 1 over what is the symbol? F double dash u. So Hamish actually made a mistake, and like I was going nuts. Okay, how is this right? Because it basically says kappa equals to mod of f double dash u, but then he corrected it later, and it was kappa equals to 1 over f double dash u. So yeah, okay, end of slides. Yeah, we are done with this. Now I can finally move to better things. Which, okay, why the fuck is it not closing? Yep. Differential geometry of curves. Am I the only one watching the stream on the side? Come on, bro. Now, if you are watching, bro, like the stream at least. All right. High order surfaces. Basic current transformations, splines, calculus. Where was it? Parameter domain. Oh, this was the 1-point compactification. I think, yeah, I covered this. But should I do it again? What's the time? I have like 30 minutes. I might as well just cover this one because the audio was fucked last time. I might as well do it again. So what is this? Well, first of all, like, why are we doing this? So this is the explanation our professor gave us, and it's like, how do you where's my eraser? How will you define this eraser? I mean, like, yeah, you can call it cuboid, and but how will you define the shape of a tree? How will you define a shape of this coffee mug or any random piece of geometry or any arbitrary geometry? Yeah, it's the same thing. Yeah, I know. How will you define an arbitrary piece of geometry? And that's why, like, the mathematicians build this shit to define surface. That's why we are studying it, because we'll have to like implement the shit in the game engine or a modeling software. So to do that, you need to understand how do you define the surfaces. And this okay, so texture domain, aka parameter domain, R2 R3. Fuck that. Well, let me just give you an example. Imagine like okay, you must have seen a globe and a world map like on a piece of paper. How do you wrap, if you like try to wrap that world map on the sphere, so what you will notice is like it gets distorted on the poles, and it gets distorted on the poles, and well, that is how you like sort of imagine mapping textures to a surface. A texture is nothing but just a sheet of paper, and like you map it on a 3D model, and that's pretty much it. And but like when you are mapping the textures, there are areas where like it will get distorted, like and like this is like an interesting fact. If you when mapping a human face, the texture of a human face, 3D model, what they do is like they put all the distortions at the back of the head, because people tend to and not on the face, because people tend to notice details on the face. They don't like the face fucked, so, and nobody noticed the back of the face or the surface beneath your feet. So that's where like they put all the distortions. Evil fucking hack. So this is just a bunch of examples, like how you can, to give you an intuition like how you can map stuff. So like imagine, let's do the easier one first. Imagine this is a square piece of paper, alright, like this is the side AA and this is the other side's BB. Like if you glue the A edge with the A edge, where's the sacrificial paper? I need to get one. Yep, the paper. So if you wrap this, if you glue the AA sides, alright, it became a cylinder, like shit. If you wrap it, like if you glue these two ends like BB after gluing AA, it sort of becomes a rubber tube or a torus or a donut, whatever you want to call it. And yeah, that's how like textures, this is like just one way of mapping texture from a parameter domain to a spatial domain. Or like how do you wrap a piece of paper on a donut model, or better ways, like how do you, like, because if you have done 3D modeling or used softwares, like you have a texture map, right? It's a square piece of paper and your model is like in a 3D space. It's a 3D object. So how the mapping is done, so like this is one way, like if you glue A and BB, you get a fucking torus. Now okay, so imagine this, how will you like wrap a sphere? Imagine if you have seen this, if you have been to bowling they clean the pinballs with this rubber sheet. You just drop your ball in it, and like you shake it like this. So imagine that same thing, and like you have this you have a rubber sheet and you put a sphere in the middle of it, and you just bring those two ends of the rubber, you glue them, and like you make a knot or something. Yeah, that's what it's called, 1 point compactification. And instead of like and if you like just lay a sphere on a like piece of paper and do this so it became like a sort of tube. Spheres in the middle, imagine spheres in the middle of it, and like you do 1 point compactification here and here, so it becomes there. That's what it's called, 2 point compactification. Imagine a toffee, eclairs or melody. Oh, melody is actually 1 point compactification. Yeah, it only has like one knot, but eclairs is a 2 point compactification. Hey, that's a good example. Genus. Oh, you might be actually thinking, why are we doing this? It's pretty useful. It's like basic stuff you need to know to do the actual things you want to. So genus is the number of handles. Do I have a coffee mug? No, fuck no. I mean, like, imagine just a coffee mug, and like genus is the how many handles can go through a surface. So if this one has like 2 handles, so we'll call it as a genus 2. And like if I only had a single handle, we'll call it as a genus 1. And if I had like 1000 handles, we will call it as a genus 1000. And that's pretty much it. And like how much time is left? 5:25. All right. So if you take if you take a piece of paper and like wrap it along these ends, it would, imagine if like these two are not corners, right? Like if you wrap along these two edges, it would be something like this. And if you wrap along these, if it's 1 2 3 4 5 6 1 2 3 4 5 6, yeah, this is a hexagon, like hexagon paper, and if you wrap around these edges, you will actually get a double donut, and double donut has a genus 2. Imagine like 2 donuts attached to each other, so it will have like 2 handles, so genus 2. You can try this out, but like our professor told us, hey, just trust me on this one. Your mind will be fucked if you try to like imagine this one. So I'm gonna take him at his word. In practice, assume we have a set of patches, pieces of R square, and we have a way of gluing them together consistently. We can assume that we have an input manifold omega that is everywhere locally homomorphic to others. Okay, what does he mean by this? I mean, like, imagine we don't have like the entire sheet of paper for the surface. We have small patches that we can twist around and do stuff to stick it on the surface of the object. We have a set of patches in R square. R square means imagine like 2D pieces of paper, and we have a way of gluing them together constantly, and we can like glue those patches together to ultimately wrap the surface. We can assume that we have an input manifold, that is, so we can assume that this single patch will behave well. That's what this thing basically means. It will behave well in the neighborhood. A surface is a set defined by a function u comma v. Okay, u comma v, I mean like 2r cube xyz, you can imagine like coordinates u comma v, like it's getting mapped from a 2D to 3D parameter domain to spatial domain. And boldface u means, I mean like I told you, like when you say bold, you see boldface is basically vector space. And yeah, and like this is this diagram of mapping from a parameter domain to spatial domain. Okay, can I cover the main thing that I wanted to today? Differential geometry, surfaces higher. Give me a second, I need to get some water. Nobody is there, so oh gosh, 1.414, yes. Hey, I'm not that good at maths. Wait, I hope this shit does this one. Okay, give me a minute. Yep. Sorry. Oh, this is the fun part. Yeah, Jacobian matrix. Let's see how much I get into this today. Oh. Okay, so N is this is like parameter domain, or like it's also called as a texture domain, and this is the spatial domain. Imagine like for the, as I was telling you before, how we map a 2D piece of paper over a 3D surface. So it's basically that. How do we how do we map that thing? So this is the 2D domain, and this is the I don't want to use 3D word, but like, yeah, spatial domain. But yeah, 3D domain. Yeah. Any surface we care about can be treated as a map of omega to r cube, meaning like meaning any surface. I mean, like, we care about, can be treated as a 2D map, as a mapping of a 2D map to a 3D surface. That's what this thing basically says. F is not unique because, as we saw just before, how, like, we were getting, we had like two curves, sorry, one curve describing two functions. Yeah, that's the right wording. We had one curve, two curves describing the spark, one curve describing this two functions, and then, like, that's why we described AFB for that. And so that's what this thing is saying, that if it's not unique, so we this mapping of, like, u comma v to xyz, u comma v xyz in, like, 3D. Assume u is fixed, we get an isometric parameter. Okay, I'll have to use a tab for this one. Come on, don't ask me my password again. Don't do this. Face doesn't match. What the fuck? Come on. Come on, boy. Come on. Okay, give me a new page. New page. How do we get the new page? Yup, so smart. Yup. Why? Yeah, I'm trying to do something. Okay, I messed up. Come on. Ah, shit. Yep. So if we, like, fix the u, come on. Oh fuck, this should be v. If we, like, fix the view, v, we'll get this curve, and if we fix u, then we'll get the curve in v, and, like, and this is called an isoparametric curve. And the same thing with the if we fix the v, we'll get you wait a minute. I'm gonna yep. I'm gonna name this as V and this one as U. Alright. And like at this point, like if you take a differentiate this isoparametric curve at like u with respect to u, we will get this velocity vector. Remember the velocity vector, how we were getting it by differentiating? Yeah, same thing. So it will be del f by del u, sorry, del v, because it will be a partial differentiation. Yeah, if you haven't heard about partial differentiation since, I don't know, 10th, 12th, well, we get to see it every now and then, and it sucks. Yeah, and this, if we do the same thing, we del f by del u. So we have the, how do I put it, at that point we have this two velocity vectors, right? And they'll be like they are perpendicular to each other, and like since it's on the surface, we are talking on, so like they will be also like tangent to the surface. So remember how we took the double differentiation of the velocity vector to get the acceleration. If we do the same thing here also, we'll get the acceleration vector, and then we get the basis. So yeah, see, del f by del v, we get the, okay, what does he mean by direction vector? So if you have a velocity vector, then velocity vector has a attached direction vector to it, because remember how speed and velocity are different, because velocity has a direction, speed is just, this is a fucking constant thing, it doesn't have any direction. Yeah, so that, and direction can be pretty useful in computer graphics. If you have direction, well, you can do a lot of shit. Constant doesn't give you anything. So like that's why we are like differentiating it to get the direction, because when we differentiate it, we get the velocity, and velocity has a direction attached to it. So the isoparametric curves in u and v are the parts of the surface. Okay, del x by del v, remember it's boldface, so imagine it's in vector space, it will have x, y, z. So this is x, del x by del v, del y by del v, del z by del v. And as computer graphics folks, we like to write things in a matrix form. It makes life so much easier. But like if you haven't seen this kind of notations, yeah, you might be thinking some sort of sorcery is going on. Yeah, the isoparametric curves in u, v are parts of the surface. Okay, yeah, we know that. Del x by del u is tangent to f v, and therefore tangent to s. Del x by del u, this red arrow, is tangent to isoparametric curve, this isoparametric curve, and therefore like tangent to s, meaning like how do you write, it will be tangent to the surface, because we are talking about the curve on the surface, and surface can be like, imagine any arbitrary shape. And del x by del v is also tangent to x. So okay, sorry, forget about the acceleration thing. acceleration thing with respect to the spatial domain. Yep, remove that bit. Yeah, I overspoke on that. Uh, so we have these two tangent vectors which are perpendicular to each other, and this del f by del u and del f by del v. Since I told you, like if you remember, like from last few minutes, if we have two vectors perpendicular to each other, we can do a cross product and we can get a third vector which is perpendicular to the both of them, and we get our fucking basis. Yeah, we care about our basis. What next? Okay, this is a spatial domain. This is a parameter domain. The same thing. Oh, this is where like it gets. Okay, what is it saying? Imagine W bar is a vector in parameter domain. Okay, and W bar belongs to omega. Yeah. U comma V naught belongs to omega. U comma V naught, I mean like this point center. What happens when we map W bar to W arrow in R cube? So what happens like when we map this vector in the from the parameter domain to the spatial domain, and like for spatial domain we are using this term W arrow instead of W bar. Look at the line LW equals to U naught comma V naught plus WRT in omega. Oh, I'm very tired. U naught V naught plus okay, this is a continuous point set and it maps to a set of S that is continuous because there's a I want the explanation somewhere. Look at the line LW equals to U naught N. Okay, this line, if you extend it, just mathematical term way to represent this LW line in omega. This is a continuous point set and it maps to a set of points on S that is continuous because F is continuous and is a curve manifold dimension 1. How do I explain? So like imagine like you have a brother and like he's an army and he's traveling from one place to another every single day. He is in the traveling mode and every single day wherever like he stops he writes a letter and sends to you, and like you are receiving a letter every single day. So if you map it on a sort of like a graph, at any given point in time, let's say from today to tomorrow, there might not be a letter, but doesn't mean he's still not traveling. He is actually is, and those like letters are mapping of 1D to R cube in on globe, and how do I put it? since the like graph of 1D is continuous at any time in the day, if he's not sending a letter, he's still traveling on the globe. So this is like this is a continuous point set, and a continuous point set can be mapped to another continuous point set. If you heard that, yeah, it might have paused off. I understand. Okay. Curve in direction omega on t. Okay. Curve in the direction, curve in this w bar vector, direction parameterized on t on curve cw. Okay, this cwt. I mean, like cwt is like the curve on the spatial domain, in the spatial domain on the surface, is given by x of lwt, which is x of u naught plus t u w plus comma v naught plus t u v w, and omega arrow equals to del by differentiation of that curve with respect to time, which gives us this thingy. I mean, like del x by del t of this, del by del t of partial differentiation of this function, which gives us, okay, so this is bold face x, like I told you, it's in a vector space, so we just expand that to xyz in terms of xyz in our matrix form, because hey, we like matrices, we like our fucking matrices. Actually, me and a friend, a batchmate of mine, like he was trying to figure out how did we get from here to here. Like, he solved it out. So you, if you want, you can sit down. You can, this will actually collapse to this. You can rearrange the terms. Yeah, and if you take the partial derivative, you will get something heavy shit, and you take the, some terms will be like sort of, you could take them out, and that's your w bar, and you get a beautiful looking matrix, which we call as the Jacobian matrix. And what this matrix basically does is it measures the distortion from parameter domain to spatial domain, like how much distortion there is when we are mapping from textual domain to the spatial domain. Okay, someone is watching, bro. If you are watching and if you didn't like this video, bro, shit will happen. पाप लगेगा बेंचो. Like the stream. Okay, what's next? Let w1 bar and w2 bar be two unit vectors in parameter domain. Cos theta is w1 bar is dot w2 bar. Okay, the dot product, fucking dot product. So like you can rearrange the dot product as w1 bar, and like you take a transpose, like put it in a matrix form and like transpose it and times w2, it will actually collapse to this w1 bar dot w2 bar. When we first saw this on the lecture, we were like, how did you write this? And then he explained. Oh, there's an explanation right there. So like if you take the w1 bar and like you transpose it and write it in this form, you will actually basically get this u1 u2 v1 v2. It's the same thing. So cos what is the angle phi between W1 arrow, W2 arrow in the spatial domain, and we represented by like cos phi equals to the dot product divided by the mod nor sorry, I've been saying mods for so many times for the last couple of minutes, but the word I was looking for, norm. Yep, I was just not getting it. Yep, it's norm. What the fuck, mod? It's norm of W1 arrow and W2 arrow. And remember how we can write this W arrow as Jacobian matrix times W1 bar, W bar. Yeah, it's basically the same thing. Jacobian matrix times W1 bar dot Jacobian matrix times W2 bar. And like Hamish said that we will leave this out for clarity, make more sense of it. So we are leaving this out. And then we do the same transpose thingy that we did, and it looks like this. And what did you do again? W1 bar. Okay, he took the transpose, like shoved it in, and it became like W1 bar transpose Jacobian transpose, and it collapses down to this, and this is what we call as the first fundamental form, Jacobian transpose dot Jacobian transpose, which actually looks like something like this. Okay, this stuff is okay, and what this basically does is measures distortion along u and v. That's what this first fundamental form does. E is the square of the distortion along curve CUV, yeah. G is the square of distortion along curve U with the V as fixed. F is 0 if and only if okay, so these two terms will be 0 only if like because these two are like we are getting the dot products, right? So the dot product is only 0 when both of them perpendicular. So this is what it means. Suppose we want, hey, come on, someone is watching my stream, like it or you will be cursed, boy or girl. Suppose we want the length of a curve on the surface. One second. Suppose we want the length of a curve on the surface. Let RT equals to this. This looks so horrifying. Yeah. Del x by del t of RT, del x by del u. Partial differentiation. Okay, I'll have to go through this one because I'm not quite sure what's happening in this part. I'll have to take a piece of paper and like go through it, but like yeah, that's pretty much it. If you even like got some intuition about it, yeah, I would say job well done, but I'm not expecting, unless you have an interest in this stuff. But hey, if you got an intuition about this stuff, like good job. But I guess that's pretty much it, and I'm the only one watching and doing the stream. Okay, I guess this is it. Bye bye. It's okay, it's about 5:55. I gotta go. Oh, maybe I'll just code on the next stream. See you guys on the next weekend. Bye bye. How do I close this thing? 14 fucking views. Wow. Crazy, bro. Crazy. Crazy. Okay, my boy. Stop streaming.